everyone. So let's start. It is my pleasure to introduce Professor Adriana Valio. So she got her PhD in astronomy at the University of California in Berkeley in 1995. She was a postdoc at Caltech from 95 to 97, and at Unicamp from 97 to 99. She obtained her Livre Docência from the University of São Paulo in 2008, and she served as president of the Brazilian Astronomical Society in the biennium of 2012 to 2014. So since 1999, she's a professor at the Universidade Presbiteriana, Mackenzie, and the coordinator of the graduate course in Geophysical, Geospatial Sciences and Applications from 2013 and 2022. She was the coordinator of the astronomy area at FAPESP until 2022, and a member of the CNPq Advisory Committee in the area of physics and astronomy until 2020. She has experience on solar and stellar activity, mainly on flares and spots, studying extrasolar planets and the interaction with their host stars, planetary habitability, in addition to radio astronomy. So thank you, Adriana, for joining us today. Thank you for accepting our invitation, and I'll let you start. Thank you.
Okay, well, thank you for the introduction, and thank you all for the invitation. It's a great pleasure for me to be here talking a little bit about my research, and which is on stellar activity and its impact on orbiting exoplanets. Okay, so first, I'll give a brief introduction on stellar activity, which manifests itself in the form of spots, flares, coronal mass ejections, and winds. And of course, all of these events are associated with convection, magnetic fields, and stellar rotation. Okay, so first let's start with sunspots. So in the sun, we know that the number of spots goes through a periodic variation, which lasts for about 11 years. And this is since Galileo Galilei and his contemporary researchers started monitoring sunspot, which started at early in the 17th century, since 1610. And as you can see here, the bottom panel is shows the, I wonder if I'll have, oh, no, I don't think I'll have the laser pointer. Anyway, so here we have the monthly number, the monthly mean of sunspot numbers, and you can see that it goes through increased variation with the cycle, as I mentioned, which is known as the solar magnetic cycle, and which lasts for about 11 years. And also, and this is since we start monitoring the solar flux in space, we started seeing that, we saw that also the total solar radiance, or the solar flux above the Earth atmosphere, also varies with the same periodicity of 11 years. Which at first glance, it seems like a contradiction, because if during a solar maximum, there are more spots on the surface of the sun, and spots are dark regions on the surface of the sun, shouldn't the flux decrease during solar maximum? Indeed, and this is not what we see. And indeed, the number of sunspot increases, but also the number of bright features, which are called faculae on the surface of the sun, and this also increases. And what happens in the case of the sun, which is considered a middle-aged star, the brightness of the faculae supersedes the darkness or the flux subtraction due to the spots. So that's why the solar flux increases during solar maximum. And similar to the sun, other stars also go through solar cycles. So here is the emission variation of the sun, which with its 11-year cycle. And then here are other 3 stars which also display cycles. And in the last century, by the end of the last century, through a period of monitoring stars for decades, Baliunas and colleagues, they monitored solar-like stars for decades, and which is called the Mount Wilson sample. And here's a few of the G stars that were sampled. And what they concluded was that 60% of the stars presented activity cycles like the sun, 15% showed variability without any obvious periodicity, and 10 to 15 of the stars showed, as this one, for instance, no variation whatsoever. And we know that the solar cycle is related to the dynamo mechanism that was proposed by Eugene Parker in 1955, which is known as the alpha omega dynamo. And but not all stars have activity, not like the sun. Not only that, but also, as I'll show in the next slide, there is a relation between age and the activity, meaning that young stars are usually more active than old stars or middle-aged stars like the sun. The sun is, even though it has this activity cycle of 11 years, it's not considered an active star when you compare it to other active stars. And so in solar type stars, age activity relation is well defined, and with young stars having very strong calcium to H and K line emission, which decays through time with the square root of the age of the star, which is known as the Skumanic law. However, M dwarfs, which are the smallest known stars, do not fit the solar type relation. And in these M stars, which are fully convective, and this is what this image here is showing, activity is more prolonged. And not only that, but M dwarfs are also more active than its solar type counterpart. And activity, now we know, is a function both of age and mass of the star. And of course, the activity goes with the size of the convective envelope. In the case of solar-like stars, with a convective outer envelope, the alpha dynamo mechanism acts in the tachocline, which is that very thin interface layer between the inner radiative zone and the convective zone. And as I mentioned before, M stars, dwarf stars, are significantly more active when compared to the sun. And here is just, and this is an image that I like very much, which was from a former master student of mine, Geisa Ponte. And what this is showing here is that young stars, let's say about an age of 50 million years old, have very active with very big spots on its surface, and with rapid rotation. And not only that, but the amplitude variation due to this rotation of the star is of the order here of maybe peak to peak of more than 10%. As the star starts to age, let's say this star here with the 2 billion years, the area of the surface covered by spots decreases. Also, the rotation period increases because the star is rotating more slowly. And also, then because there are less, the spot area is smaller, you see that the amplitude variation here decreases. And then a star like the sun with about 5 billion years old, then you can hardly see here, let's say, the period of 27 days, which is the rotation period of the sun, and the amplitude is very small. And here is just some plots showing this relation between the magnetic activity, which is called by the dynamo, and rotation of the star, which is an indication of the stellar age, meaning that young stars are rapid rotators and older stars rotate slower. And here are 3 plots showing the calcium emission line, this X-ray flux, and the unsigned magnetic flux inferred from Doppler, Zeeman Doppler imaging. And here is different ways of measuring the rotation period. Age increases to the right. So you can see here that all of this, sometimes smoothly, sometimes with a break. So the activity decreases with age. Okay, now let's go to the activity characterization, and mainly spots. So in the sun, spots were the first. Here, the spots were the first indicators of magnetic. Why doesn't it want to stay there? Of magnetic activity. As I mentioned before, they are the cool regions on the surface, on the photosphere of the stars. And they're about like maybe 1,000 to 1,500 degrees cooler than the rest of the photosphere. And of course, we believe that other stars, just like the sun, will also have spots on their surface. However, the current technology and the telescope do not have the spatial resolution to detect these spots, by taking a picture. But there are methods to detect spots on the surface of the star. And basically, here I'll briefly talk about 3 methods. The first one is Doppler imaging, which you can do through spectroscopy. You can measure an iron sensitive or a magnetic sensitive line, such as iron or nickel, and you will see the deformation on the line due to the presence of spots as the star rotates. And then there is the photometric modulation, which I mentioned before. And what you're seeing here is the light curve observed by the Corot satellite of the star Corot 2. And what you're seeing here is the rotation period of the star, which is about 4 to 5 days. And these are the transits of the Jupiter, the hot Jupiter planet, which orbits Corot 2. But you can see here this modulation, which is done through high precision, which is detected through high precision photometry. And here is a method that I devised. I was the first one to propose in 2003, which is, what if the planet, while it's transiting, occults a spot on the surface of the star? Could we detect the spot on the transit? And if so, can we obtain the physical characteristics of these spots? And I'll talk a little bit more in more detail in a few minutes. So first of all, the first method, which is Doppler imaging. And here, what you're looking at here is the line, and you can see the deformation. Oh, I don't know, my mouse is going crazy, I'm sorry. Okay, and you can see here, on the left panel, the deformation of the line as the star rotates. This method, it's very good for large star and fast rotators. And you can do an image of the surface of the star. And you can see on the right panel, images showing bright regions and also this very large polar spot on HT 12545. And it's much larger than the sun. You can see the sun up here on the plot. The photometric modulation is the same thing. The star is rotating. Spots come in and out of view as the star rotates, and we're looking at different hemispheres, as you might think, of the star. And then you will see this variation in the flux. More spots, less flux. Less spots, brighter the star is. And here, this also is valid for stars younger than the sun, because as I mentioned before, older stars have facula dominate, the brightness of facula dominate over that of those of spots. So, but the stars that I'll be talking about here are all younger than maybe about 2 to 3 billion years. And here is just another light curve of Kepler-17, which was of the star Kepler-17, which is a G-type star observed by the Kepler satellite for 4 years. And here is the method that I devised, which is today is known as transit mapping. And that's the idea. There's a spot on the surface of the star, the planets transit in front of the spot. And what you see in the light curve, of course, the light curve decreases by about 1% for a Jupiter-like planet once the planet enters the bright disk of the star. But when it crosses a darker region, which is the spot, then what you see is a slight increase here, or a bump, if you will, during the transit. And here are just simulations that I made. Here is a solar image of an image of the sun, and then here is an active region, a real active region. And here I did two simulations, one with a Jupiter-like planet and one which you don't, I bet you can't even see, but there is an Earth-like planet here. And what you can see is that, first of all, the transit here is, you can look at the y-axis, is 100 times smaller for an Earth-sized planet, which has a size, Earth radius is 1/10 of the Jupiter radius, which is 1/10 of the solar radius. But here you can see that the bump is less well-defined, and here is not only it's well-defined, but you can even see that there are actually more than one spot in this active region. Well, here's everything's blurred. Anyway, okay, so here's the model that I propose. It's called Eclipse. And you just make a 2D image of a star, which is link darkened, and then a circular planet passes in front of the star. And depending on its, first the planetary radius and the orbit parameters, then you have transits of different durations and depth. And of course, and so you have to give like the semi-major axis, which is of course related by Kepler's third law to the rotation, to the orbital period of the planet, and the inclination angle of the orbit. Not only that, but we can also include spots on the surface. This program Eclipse, you can also include spots on the surface of the star. And then once the planet passes in front of the star, you will see the bumps that it will cause on the light curve. And the spots are basically parameterized by 3 values: the intensity with respect to disk center, its size, and its position, which is given as a longitude and latitude on the stellar disk. And here's just an example of a light curve fitting for Kepler 17. And what we do first is we fit, this is the dashed line here, we fit a model without any spots, and then we subtract this model of a spotless star, and we get the residuals, and then you can see here 3 very clear bumps, which are caused by the transit of the planet in front of these 3 spots. We do an MCMC fitting, and then we get the parameters of the spot size and intensity and the location for these 3 spots. And the spot transit mapping has been applied to these 9 stars so far. And here are the G, K, and M stars. And here are the different authors. Okay, then the stellar activity impact. So the first impact of the stellar activity on not on the habitability, but on the characterization, for instance, of stellar atmospheres, excuse me, not stellar atmosphere, exoplanet atmospheres, that I'll talk about is the transmission spectrum of an exoplanet atmosphere. Once the planet is transiting in front of the star, if it has an atmosphere, then what would happen is that the depth of the transit will depend on the wavelength. And the planet has this atmosphere, the edge of the disk is going to be a little bit fuzzy. And then once the planet is transiting, so here is the planet and then the atmosphere of the planet with different molecules, composed of different molecules. And when the light from the star passes through this atmosphere towards, the satellite Earth, the space mission, the telescope, then what we'll see is that the transit depth is going to depend on the composition of the atmosphere and the wavelength, as I mentioned before. Here is an example of a transmission spectrum of exoplanet GJ1132b, which was observed with the Hubble telescope. And as you can see here, here is what's measuring is the transit depth. And so this gives you the size, let's say, of the atmosphere. And because it's according to wavelength, it depends on its, as I mentioned before, on its constituents. So let's say here is a line of methane, hydrogen, cyanide, and here's another line of methane. And then here just some aerosol scattering of aerosols, which are on the top of the atmosphere. This is, oh, by the way, this is a rocky Earth-like planet. And through studying the composition of the atmosphere, it was, we concluded that the atmosphere is secondary. It's not the primary. So it's probably through volcanism or some kind of mechanism that this atmosphere got to be what it is today. And my current PhD student, Victor Sumida, he's studying the impact of spots on the transit depth. Because if we want to do a spectra, a transition spectra with high precision, because we're measuring transit depth and we know that spots affect the transit depth, then we need to know, we need to quantify how much the spots will affect the transit depth so that we can subtract this effect and get a real or a good, precise spectra of the composition of the planet atmosphere. And so the first thing that Victor did was include wavelength dependence on the eclipse model. And he considered both spots in the transit core that would be occulted during the planetary transit and spots outside the transit core, which we call unocculted spots because the planet will not pass in front of them. So here, for instance, the planet, and we're looking from Earth from this side here. And then you can see this spot will be occulted, but not these. And oops. Okay. And so the first thing, well, something went wrong when I migrated from from my presentation from one computer to the other, but nevertheless, so what's going on here is both the stellar photosphere is modeled as a black body as well as the spot. So here is an atmosphere of a star that has an effective temperature of 5385 Kelvin. And then here's a spot which is about 1500 cooler than the photosphere. So this is the spectrum. And at 5 wavelengths, so here are the wavelength. This is what, let's say a big spot here close to the center of the stellar disk. And not only that, but also we know that the limb darkening also varies with wavelength. So this is what you're seeing here. And then of course, the difference in intensity at different wavelength of the spot will vary. So what he did was, as I mentioned, he incorporated wavelength dependence onto the onto the model. And so here is a simulation of transits at different wavelength. And you can see that not only the depth of the transit varies, but also the shape of the transit. And here we're not considering any spot yet. So, so here is, but here is what happens when here is just the photosphere without spots. So this is what the transit depth of a transit of a Earth-like planet like DJ1132b. This is the transit depth just from considering, as I mentioned, the wavelength dependence. But if we consider an occulted spot, which is of a radius of about 1/10 of the stellar radius, I think it's 1/10. no, not the radio within the tent. I'm sorry. It's blocking about 1% of the stellar photosphere. Then this is what we would get. So you can see that the depth will get shallower than what we would expect if there was no spot. And so, I'm sorry. So here what you're seeing is the spectrum of GJ 1132. And so maybe here if we consider, we would have to consider, you know, like the spot, maybe there is a spot, an unoccluded spot that is causing this increasing here, which has to be taken into consideration before we start. Oh, these are the data, the crosses are the data. And then here are different models which are given by these lines here. Not only that, but what also another interesting result that Victor found was that depending on the transit latitude, this inclination or this variation of the depth with wavelength varies. So here are for different transit latitudes. No, here's the star, so the planet can transit across the equator, or it can transit latitudes from 0, which is the equator, up to the close to the pole, which is close to, so here you can see, here's very close to the equator, which is the red line. But then here is a very latitude of 63 degrees, which is close to the pole. And you can see that this varies. So this also has to be taken into consideration. Okay, space weather, a little bit about space weather. So when radiation, in the case of the solar Earth, Sun-Earth connection, so when radiation and particles, which are produced by solar activity, usually the radiation is during solar flares and the particles are during coronal mass ejections. When these particles and radiation reach the Earth, they may cause a lot of damage, like lethal doses of X-ray radiation through astronauts, which are unprotected outside the space station. They will alter satellite orbits, causing sometimes the satellites to fall back on Earth ahead of time. And in January of this year, SpaceX lost, I guess, 40 out of 49 or something satellites from a major, not even a major, it was not even that big solar coronal mass ejection that happened at the end of January. And geomagnetic storms, which causes the geomagnetic field of Earth to go haywire, ionospheric alterations, which will affect long distance communications, current peaks in transmission lines, blackouts, erratic behavior of navigation instruments like compasses, and ozone layer alterations, auroras. They will influence the signal between satellites on Earth, or even GPS signals are one of them, which will be affected. And even your phone communication, you know, like cell phones, if it's through satellite, it might be affected by solar activity. And what about exoplanets? Well, of course, all of these that I mentioned, except for the auroras, on the ozone layer alterations, all of these are impacts in highly technological society. But not only that, for exoplanets and very active stars much more active than our sun, their winds, coronal mass ejections, flares, and ultraviolet radiation from all this activity, from flares, for instance, can cause atmospheric erosion, photoevaporation of the atmosphere, and affect a planet habitability. So here is just to show how this can be affected. These are observations of planetary transits in the ultraviolet. And what these authors detected was that the transit depth was larger in the X-rays than it was in the optical, meaning that the planet had an extended atmosphere which was hot and absorbed the X-rays. As I mentioned, ultraviolet radiation from the star can cause photoevaporation of the planet atmosphere, especially for these exoplanets, which are so close to their host stars. And here is an actual observation of such. And you can see here a very asymmetric transit, which probably indicates a dusty tail, like a comet-like resulting from the evaporation of the planet atmosphere. And here, just simulations and observations of what the transit would look like and how it would be asymmetric in the ultraviolet of the transit of HD 209458, which was the first planet whose transit was detected before its rate of velocity variation of the star, and in 2000. What about the winds, stellar winds? So here is a simulations, particle simulation of the 5 planets in orbit of the star Kepler-11. And this is the closest planet. And as we go from this planet to here, that's the planet which is further away. The size of the planet is shown by the dark spot here. And the blue dots are the planet atmosphere, and the red dots are the particles from the wind of the star. And you can see here that for the further away planet, which is not that far away when you think about it, it's about a quarter of the Sun-Earth distance. The atmosphere is basically intact. However, for the closest planet, which is only at 0.09 AU of the star, then you can see how ion pickup from the stellar wind can actually deplete the planet of its atmosphere. And here's another observation of WASP 12b. And what you can see here is a bow shock of the wind, of the stellar wind interacting with the planet, maybe the planet magnetosphere or something, or even if it hasn't a magnetosphere, but just, like the interaction of the stellar wind and the planet will cause such such feature. And you can see here in green is the ultraviolet transit, and then here are the data showing that there is something going on which actually increases here, and showing that there is a bow shock there. The ejection of mass from the corona of the star, which happens in the sun, associated with the stellar activity. And here are some MHD simulation showing here at 3 different times after the ejection of mass, which goes through the planet. And you can see here how the atmosphere of the planet will be carried away by this large quantity of mass that is ejected from the star, which is sufficient to tear off the outer part of the planet envelope. And flares. Okay, so here I'll just talk a little bit more about flares, because this is the work that a student of mine, which I'll talk briefly, did during her PhD. So first of all, Kepler has observed, it wasn't the first one. There were other stars which were observed, which flares were observed before, but Kepler, due to its 4 years observation of continuous observations of 150,000 stars, showed that there are almost 10,000 solar type stars which are flaring. And when I talk about flaring, I'm talking about super flares. That is flares which are about 1,000 to 10,000 times more energetic than the largest solar flare. And 365 super flares larger than 10 to the 35 ergs were detected in 148 stars. The largest solar flares detected so far reached 10 to the 32 ergs. So here we're really talking about things which are much more energetic. And you can see here that this is the spot modulation of the star. Usually flaring stars are stars which also show the presence of spots. And then you'd see that here are 8 times in day. So for a few hours, you would have this strong peak where the brightness of the star will increase by a large amount. And so here are the super flares observed by Shibata, or in this work of Shibata et al. And you can see that they're just a continuation of, this is just flare frequency against flare energy. And you can see that these are the largest solar flares, and then the regular solar flares, microflares, nanoflares. These are from the sun. And then here are the super flares. So they're just about the same line that we see for solars. So they do seem to be the high energy counterpart of solar flares. And here's the flare frequency of stars. So even though M dwarfs may not produce that stronger flare, they flare much more frequently than solar-like stars. So you can see here is from the different spectral types of flares, and you can see the amount of, so here active G dwarfs, they do produce, and active K dwarfs produce the largest amount, the higher energy flares. But M dwarfs will produce more flares. So as I was mentioning before, a former PhD student of mine, Raíssa Estrela, who is now a postdoc at the Jet Propulsion Laboratory in Pasadena, she worked, as part of her thesis, she worked on more, her thesis was more than that, but I'll be talking about the biological impact of super flares on planets in the habitable zone. And why should we care about super flares on the habitability? Well, because super flares release significant amounts of X-rays, extreme ultraviolet and ultraviolet radiation. And depending on the energy of the flare, it can cause changes in the atmosphere, such as I mentioned before, atmospheric loss, and also alter the chemical composition in the atmospheres. Not only that, but the protons that arrive from the flare, the high energy particles, the energetic, almost relativistic particles, can also produce odd nitrogen and odd hydrogen in the upper stratosphere, which will destroy ozone if there is ozone in the atmosphere of these planets. And of course, this will affect then the origin and evolution of life. And well, did this young sun also produce solar flares? And if so, well, if it did, then we believe that the effects were twofold. They could be both positive and negative. As positive, we can mention that at the beginning of life, change in the atmosphere and producing more greenhouse effects, like to warm up a little bit of the planet, could be a positive thing, because the young sun was only about 70% as bright as it is today. But of course, on the negative side, this very strong or super flares could produce high doses of ultraviolet radiation, which is not good for life. So here there were 2 papers. One of them, the first one, which studied the habitability or the effect on the habitability of a hypothetical planet on orbit, in an Earth-like orbit of Kepler-96, which is a G star. It's a solar-like star. It's a G star, very much like the sun, but it has half the age of our sun. It has about 2.2 billion years. It's only about 2.2 billion years old. And then the effect of the activity of the M dwarf TRAPPIST-1 on its 3 planets in the habitable zone. Just to mention, Kepler-96, the star has a planet, Kepler-96b, which is a hot super Earth, okay? It's very close, so it's not habitable at all. We're talking about an Earth-like planet at the distance of 1 AU of Kepler-96, a hypothetical planet. And here we did the following. So there are basically 2 stars, TRAPPIST-1 and Kepler-96. We observed the flare in the optical. We observed this. These observations were done by Kepler, integrated over the continuum, the visible continuum. But we want to know how much ultraviolet was produced in these detected superflares. Okay, in order to do that, for Kepler-96, which is a star very similar to our sun, I don't know if it's a G2, but it's very close. Then we use the strongest flare detected in the sun, and we know what the ultraviolet flux was. For the TRAPPIST-1, which is an M dwarf, we used another M dwarf, which had flares detected in the ultraviolet, and that was 80 Leo. For the planetary atmosphere of the 3 Earth-like planet in the habitable zone of TRAPPIST-1, we considered, and also for this hypothetical Earth-like planet in the habitable zone of Kepler-96, we considered 2 types of atmospheres. An atmosphere like the present Earth with ozone or oxygen, and an Archean atmosphere. Why Archean? Because the Kepler-96 has 2.2 billion years. It's 2.2 billion years old, and that's when the Earth was this age, it had an Archean atmosphere without oxygen. And then we calculated what would the ultraviolet flux be at the surface of the planet. Once we know there was the super flare, which produced ultraviolet, and then this ultraviolet radiation had to flow through the atmosphere and was attenuated, but how much would reach the surface? And then estimated the biological impact of this ultraviolet flux at the surface onto bacteria. An Escherichia coli, which is a bacteria that we all have in our guts. It's a very common bacteria. And Deinococcus radiodurans, which is an extremophile, which can support extreme doses of X-ray radiation. So again, why Kepler-96? Because it has the age, the 2.2 billion years old it's about the age on Earth when the first algae started producing oxygen. So that's known as the Great Oxygenation era in our planet. So before that, there was hardly any oxygen, and after that, there was enough oxygen for the first multicellular organisms to start producing, to be created here on Earth. And so that's why this star can be used as a proxy to understand what would the primitive Earth environment be, and what would the conditions in a planet in the habitable zone of the star with an Archean condition. Okay, so here first Kepler-96, we detected one very strong super flare, which had an energy of about 1.810 to the 35 ergs. And you can hardly see, but here is a transit. The flare, all the 3 flares occurred during transits of Kepler-96b. As I said, it's a hot planet. We're not talking about this. We're not modeling this one. But then there are 3 flares, 2 flares with energy of about 10 to the 33, and 1 super flare. And here is the composition of the Archean atmosphere that we model for the planets. And so the Archean, 80% nitrogen and 20% dioxide, CO2 and carbon. And the present day, also 80% nitrogen, but 20% oxygen. So these are the 2 compositions of the atmosphere. For the case of Kepler-96, which is a G-type star, we use the solar flare which was an extreme event which occurred on 28th of October 2003, and we saw that 12% of its flux was in the ultraviolet. And so in the case of the super flare, we would have an increase of 5,400%. And what you can see here is the spectrum of the flux, the ultraviolet flux. So in black is the ultraviolet flux of the star. And then here, what it was the flux at the top of the atmosphere of the planet with the flaring flux. And so here's the present atmosphere, and here is the flux, the stellar flux, which reaches the surface on a normal period and during this very strong flare. And in green is what happens with an Archean atmosphere, which has no oxygen, which has no ozone. So there is no absorption of the ultraviolet at the top, the high atmosphere. So you can see then that this shorter wavelength, which are known as the damaging ultraviolet radiation, will reach the surface. Okay, and then again, the normal brightness of the star, and then with the flare. And of course, we had to consider the biological impact on these bacteria. So we had to know what the response of this bacteria would be, through radiation at different wavelength, and this is called the action spectrum. And what we know is that DNA is mainly damaged in the UVC and UVB range, which is about the 200 to 300 nanometers. So here is okay, UVA is okay, but this one is really damaging to DNA. And then we did all the calculations. And so here are the results. Here, the top of part of the table, this table is for the very strongest super flare of 10 to the 35 ergs. And then here, the bottom part is for the other two flares, which are 1,000 times less energetic. And here are actually three models. No atmosphere whatsoever. So this would be like a moon-like atmosphere. And then an Archean atmosphere and the present day atmosphere. And this is the flux or the effective irradiance, the biological effective irradiance that reaches the surface of the planet. And what are the tolerances of these bacteria? So the flux dosage, the maximum flux dosage, the minimum flux dosage, which will cause a 90% death of the bacteria, or in other words, 10% survival, for Adenococcus radiodurans is 553 joules per square meter. This Escherichia coli has a smaller tolerance of only 22.5 joules per meter squared. So we can see that these numbers are larger than these two thresholds. So in the case of no atmosphere, no bacteria would survive. In the case of an Archean atmosphere, Adenococcus radiodurans could survive for the less energetic flares, which still, I remind you, are 10 times more energetic than the largest solar flare. But in the Archean atmosphere, it would also not survive. And of course, if there is ozone, or if there were ozone on the atmosphere of this hypothetical planet, then everybody would survive, everything would be fine. Okay, so we know that on the Earth, which even if the sun was like Kepler-96 and produced flares like with energy of 10 to the 35, we know that life survived and thrived here on Earth. So, okay, so how can we go about, fixing this? Well, what about life in the ocean? Okay, so what we consider here is that, well, what about if these bacteria are underwater, even it could be a lake or it could be an ocean, and so that the ultraviolet radiation that reaches the surface of the water would be further attenuated throughout, like a layer of water. So here is how how this radiation would be attenuated. And then we estimated for both bacteria. And what we can see is, and here for the 3 flares, so here's the strongest flare in green. So Escherichia coli would be fine if it were, we know it's not a bacteria that lives in the sea, in the water, but anyway, a bacteria with a similar tolerance in the water, or a single cell organism. It would be fine if it was below 28 meters. So all that damaging ultraviolet radiation would all be absorbed within 28 meters of water, depth of water. For the Deinococcus radiodurans, this depth is smaller. Only 12 meters would be sufficient for survival of the bacteria. Okay, what about for the TRAPPIST-1 system? So now we're changing stars. It's not a solar-like star. We're not talking about the past of the Earth. We're talking about a different system, which has an M dwarf, an M8 red dwarf, which is a star less than 10% of the radius of the sun. And as you can see here, the whole system, it has 7 Earth-like planets in orbit. And this is what it looks like. And then there are 3 in the habitable zone shown by this green ring here. And the whole system would fit in this small ellipse here, much smaller than the orbit of Mercury. But nevertheless, it's a much smaller star, so the flux is much less than that of the sun, which means that the temperature on the surface of these 3 planets would be between 100 degrees Celsius and 0 degrees Celsius. So if there is water, it could exist in liquid form. And it was observed by the K2 mission with the Kepler satellite. And there were, in about a period, I guess, of a little over a month, there were 47 flares detected between energies of 10 to the 30 to 10 to the 33 ergs. You can see here, there were many more flares, but the energy was smaller. So the largest flare here was 10 to the 33. And here is the light curve of this flare. And again, present day atmosphere, present day without ozone, and then an Archean atmosphere. And this is the flux at the top of the atmosphere. And again, flaring and non-flaring. And what we did here is, instead of using the atmospheric attenuation model from O'Malley and Kaltneger, we used a GEONT4 radiative transfer code for that. And so here, and each curve here is a different time during the flare. So all these points here, different times. So of course, different fluxes. And again, so here is the star, the flux of the star at the top of the atmosphere. And here is with the present day atmosphere with oxygen or an ozone layer. And then here is an Archean atmosphere. And here again, wavelength. So this is, again, the part which is damaging to ultraviolet, the ultraviolet flux is damaging to living organism. And again, the similar table only for this largest flare, which was 10 to the 33 ergs. And again, the same result. No bacteria will survive without ozone, and both bacteria will survive with ozone for the 3 planets in the habitable zone. Okay. What about if under the water? Oh, oops. Oh, I skipped one slide. Well, under the water, both bacteria would also survive on depth which were less than 10 meters. So everything's fine here. And again, and to summarize, so the stellar activity impact I've talked to you about how the atmospheric composition can be how the spots, the occulted and unocculted spots can affect the transit depth measurements, which are used to infer the composition of exoplanet atmospheres. So it's important to characterize especially the unocculted spots. And I talked a little bit how ultraviolet radiation can photo evaporate the atmosphere of an exoplanet, as well as coronal mass ejections and wind will also cause atmosphere erosion. And lastly, I talked about how flares and its ultraviolet radiation can provide lethal dosage of ultraviolet radiation on the surface of planets in orbit, even if they are in the habitable zone. And so thank you very much. Obrigada. And the Eclipse code is available in Python through this GitHub, and I'll also leave it with my email. Thank you.
So, thank you, Adriana. Do you hear me? Thank you, Adriana.
Barely.
Okay, so questions for Adriana? There is one question here. If you cannot hear it, I will repeat it for you.
Yeah, early on in your talk, you showed a histogram of the flare frequency as a function of flare energy for M stars, K stars, G stars, and then for, separately, the sun. And I'm wondering, the sun seems to be quieter, and why is the sun quiet? Is there something special about the sun that makes it lower than the average for the G stars that you plotted?
Which plot was that? You're talking
about 1/3 of the way through your talk. It's a histogram of flare frequency on the y-axis and flare energy on the x-axis. Yeah,
okay.
I just saw it. There.
This one.
Yes.
Uh-huh.
Yeah, so the sun is significantly lower than the G star average. And my question is, why is the sun quieter? I've heard that the Kepler calibration was messed up a little bit because the sun was quieter than they thought it would be. But I'm wondering, is it safe to say that the sun is quieter than the average G star? And if so, why?
I would guess that it's because of its age.
So
it's not considered an active star. And so probably these results are biased towards active stars, which are probably younger. So activity not only depends on the mass, but also on the age. And here we're just seeing a cut through mass or spectral type.
So you think the G dwarfs that were used to make that plot are on average younger than the sun?
Yes.
Okay.
Other questions? Adriana, there is another question there. I'll take the microphone.
Okay.
Hi, Adriana. Thank you for the very nice talk.
Thank you.
Do you think that the alteration, the chemical composition in the exoplanet's atmospheres due to the super flare could cause thermal inversions? And how could that affect the planet's habitability?
I didn't understand everything because of the sound. So you're talking about how the flare radiation would affect the composition of the exoplanets, and if that could alter. I missed that part.
Yes, and if that could cause thermal inversions, and how
thermal inversion?
Yes.
Okay.
And how would that affect the planet's habitability?
Well, again, it's any impact of flaring would be a temporary impact. It would be something that would last for a few hours. I mean, usually flares, they last for not even like at most 1 hour. So the impact would last, I mean, the cause would be 1 hour, of course. Once it changes the composition, then that could be that could last a little bit longer. But I don't think it will last more than days. Even like on Earth, coronal mass ejections, they cause geomagnetic storms, and they alter the geomagnetic field of Earth for about maybe 1 day or a day and a half, not more than that. So I don't know how to estimate, even if it did cause a thermal inversion, which I'm also not sure if that would be possible. How if that thermal inversion could last for maybe 1 or 2 days, how that would affect the habitability. I don't think that would have a very strong impact on habitability, which is different from ultraviolet radiation, because then, like just one, how do I say, flash or radiation dosage can really, that's how we sterilize things here on Earth, right? We can use ultraviolet radiation to sterilize something. You just flash the ultraviolet for a small amount of time, and that will kill bacteria. I don't know if thermal reversion would be that hazardous.
Okay. Other questions?
Yes. Adriana, concerning, for example, the TRAPPIST-1, probably the exoplanets that are in the habitable zone, they are tidal locked. So if you have a flare or super flare, this will affect the whole planet or just the hemisphere that is facing the star?
Well, if we're talking about ultraviolet radiation, then it will probably only affect the hemisphere, which is facing the star, right? Because then the other hemisphere wouldn't receive the radiation dosage. So yeah, I think let's say the nighttime or the night hemisphere would be safe from that. But that from the flares, but like the other effects, like from atmosphere erosion, then I guess the whole planet will suffer, because even if, like it would just stream.
And I have another question. You show a slide with the transmission spectra obtained by Hubble for an Earth-like planet. I don't remember the name of the exoplanet. But you said that probably the atmosphere is not the primary atmosphere, but probably is a secondary atmosphere. How is it possible to say that?
Oh no, that's simple. The primary atmosphere usually is considered to be hydrogen and helium. Like the Jupiter atmosphere and like the giant planet's atmosphere. That's considered a primary atmosphere, which was formed with the planet. And so if we don't detect large quantities of hydrogen or helium, then that means that this just like the Earth, what we have here is a secondary, not even considering the oxygen, which is due to living organism. But the primary atmosphere was lost right in the beginning. They're very light gases, so the gravitational field of the planet cannot hold it, and so this primary atmosphere was lost. And then through volcanism and other kinds of an impact, like on the rocket on the solid surface of the terrestrial planets, then that would generate the secondary atmosphere.
Okay, thank you.
But not only that, but depending also on the type of gases that were detected, then we can know if we may know if they were due to volcanism or other kinds of processes.
Okay, thank you.
So other questions for Adriana? There is another one.
Yeah, you showed a transit of some sunspots in the Kepler data. I think there were 3 sunspots that you showed in one of the early slides. And I'm wondering what fraction of Kepler planets detected in transit have sunspots that that's right. So that's one example out of, but there are, thousands of Kepler planets. How often do you see that?
Okay. So I showed you also, which was the next slide, like this kind of work this method was applied to so far to 9 stars. It's not that common, but what we first look for, or what my students first, which I ask my students to search for, is the modulation on the light curve. So we look for stars with transiting planets, which has a strong modulation in the light curve, modulation of a few percent, or at least 1%. And then when we look at the transits, we see this. And like for the Kepler 17, which is, I think the orbital period, it's a short orbital period, and there are many transits. We detected like about 1,000 spots just on Kepler 17, which was the most spotted star that we studied from like this list. But like on the other list, like Kepler 411, it's about 100 spots. And the nice thing about Kepler 411 and Kepler 210 is that this one has 3 transiting planets, and we detected spots on all of them. The transit of the 3 planets, and also Kepler 210, it's 2 planets, and we also detected spots on 2 transits. So we can see spots on different latitudes. We can measure differential rotation and interesting stuff like that. But let's say it's not that. First of all, we need to find an active star, which is a star which shows, and I'll go back to Geisa's plot. So we search for this. And then once we see this and there is an orbiting planet, then we go and look at the transit, and we usually find those bumps.
But if the star has a lot of small spots, then you won't see that modulation during non-transit. So
You're right. Mm-hmm. Oh no, yeah, the spots that we detect on these stars, they usually 4 times or even 10 times larger than solar spots. Or even active regions. We're probably not seeing a single spot, but we're seeing an active region, like a clump of spots or the group of spots.
You also
But
mentioned,
yes, you're right. If the star has isolated small spots, it will be hidden within the noise of the data.
in the beginning of your talk, you said that the irradiance, or the luminosity of the sun, is brighter when there are more sunspots, and you pointed out that was probably because of the facula. Do facula play any role in when they're eclipsed, or are they too spread out to play a role?
Yes, this one paper here on Kepler 71, we detected faculae. What would the signal of faculae be? I don't have a plot here, but I will show. What happens here is if this was a faculae instead of a spot, it would mean that it was brighter than the surrounding photosphere. Then what we would see is a valley. Instead of a bump, we would see a decrease in the light curve. And we saw a few on Kepler 71 transit, Kepler 71b transits. We saw much more spots than we saw faculae, but we did detect a few faculae.
Thank you.
Okay, so I think we can thank Adriana again.
Well, thank you.